Yeah. So good morning guys, welcome to this last session of this particular subject, fluid mechanics and hydraulic machines in this fast track course. Okay, and today is lecture number 14 and we will actually conclude this particular subject in this lecture. Okay, and in this lecture we'll basically look at a bit of turbulence. Okay, so what are different equations that you can understand basically from the turbulence, and also we'll look at Euler's equation of turbo machines. Okay, not the Euler's equation what we have seen for the normal momentum analysis, we'll look it for the torque analysis. Okay, so we'll see the Euler's equation of turbo machines, and then after we'll also see a bit of impulse and reaction machines. Normally in gate we have only turbines, of course, so we will see about impulse and reaction turbines. Okay, and always we'll also solve certain numericals. Okay, so this is the way that we are going to move ahead. Now if you see, in last lecture we have talked about dimensional analysis. Of course, we have also talked about concept of drag and lift, all these things, but in a major way, we have talked about dimensional analysis. In this, I have explained you two fundamental techniques. One is the Rayleigh's method of doing this particular dimensional analysis, and the second, most important, Buckingham-Pi theorem method. Buckingham-Pi theorem method. Okay, so this is the Buckingham-Pi theorem method. And this method is very powerful, that even we'll use this method even in today's class for talking some things about hydraulic machines. Okay, so in hydraulic machines, normally, you know, whenever you want to install a turbine, it's not possible for you to test a full scale turbine. Okay, so what you will do, you will actually model the turbine and then you will, you know, look into the thing. So we will see this Buckingham-Pi theorem method in actual case. Okay, and also I would like to say, in last class we have seen certain dimensionless numbers. Okay, now these dimensionless numbers we have majorly talked about, I think 4 or 5 numbers. Let's say Reynolds Ford number, then after we have talked about you know, like Weber and Euler's number, and also we have talked about Mach number, right? So we have talked about these particular dimensionless numbers in the last lecture, correct? So are these things clear to you till this point? If it's clear, we will see a bit of turbulence and also hydraulic machines, some basic introduction to hydraulic machines or turbo machines in this particular class. Okay, so is that clear to all of you? Yes or no? So please type in the chat box. Is that clear to each and every one of you? Yes? Okay, so let's continue here. In today's lecture, first of all, we'll talk about turbulence. Okay, so turbulence, as you know, disorderness or ediness in the flow. Now, one thing that you can understand here is, whatever the analysis we have done for the laminar flow, same analysis equally holds here, but at the same time, the one important point here is things won't remain steady. These are highly unsteady flows, because whenever there is a turbulence, you can see things actually keep you know, changing very frequently. Okay, and because of this unsteadiness, everything is dependent on time, and generally we focus much on the averaged values. Okay, so like for example, in case of laminar flows, what happened, let us suppose if a fluid particle is moving, once you make a steady assumption and once you keep the things steady, then what happens, the fluid particles continues to move in a particular fashion or in a particular, you know, understanding. But here in turbulence, the particles keep on mixing and there could be a lot of physics which continuously changes. So everything what we do is, we'll take, because of this unsteadiness, we take time averaged values. Okay, like for example, if you take two velocity profiles, I'll just try to tell you one thing. If this is time and if this is the velocity at a given section, for example, then with time, normally in case of a laminar flow, what happens, this remains constant like this. Okay, normally the fluid particles keep moving and the velocity at any particular section, under steady assumption in case of laminar flow, the velocity remains constant with time. But in case of turbulent flows, the situation is slightly different. If this is time axis and if this is your velocity axis, then at any given section with respect to time, velocity actually fluctuates a lot, correct? There are a lot of fluctuations which actually takes place. So it's a fluctuating velocity actually. Okay, so this is normally the case of a turbulent flow, and this velocity what I have done, this u, is basically observing velocity of particles at a particular section over some period of time, okay, because things keep on changing with time, so we are interested much on average. Okay, now here it's study, but here it is moving very hard. So normally if you see u is function of x, y and t in general, it depends on x, y and t, and once you fix the section, these two are fixed, then this keeps on changing with time. Yes, correct, because at a particular location, at a particular section, you can fix this coordinates x and y, and then with respect to time, what is the change in u is nothing but this graph. Now to analyze turbulent flows, what we physically do is, we'll see in turbulent flows, since you can observe u is not fixed, okay, so u is actually taken as some mean velocity plus u dash at any given time. Okay, normally this t is a function of time, correct? So what we do is, we'll split this u into two parts. One is the time averaged of this part, like for example you can see this we can call as u bar actually. Okay, so this is the mean velocity, so this term here is, this is your u bar actually, okay, which I have written here. Now clearly I'm telling you u bar is the time averaged velocity, correct? So u bar is time averaged velocity. Now for example, let us suppose if I observe the velocity variation up to a time capital T. Okay, so let's say I have observed this variation up to a time capital T. This is time t is equal to 0. I have started the observation at this point. Then if this u bar is time averaged velocity, what we can do? Can we say u bar is nothing but 1 by t, because you can see the dimension wise, this is nothing but u dt integral from 0 to t, and this gives you the total area under this curve. So if I divide with the total time interval using mean value theorem of integration, you all know mean value theorem of integration. Have you used mean value theorem of integration anywhere? Come on, please type in the chat box. Have you seen mean value theorem of integration, and have you used it anywhere in your mechanical subjects? It's okay. If it's yes, please say yes. If it's no, I'll tell you what is mean value theorem and also what are the uses of it. Normally in single variable calculus, we go through that mean value theorem of integration, which is again one of the fundamental theorems of integration. The chart is delayed, I guess. Just a minute. Lag is a bit high, I think. Yeah. Okay, nothing much. Fine. Okay, so let's see what is mean value theorem of integration is. See here. Mean value theorem of integration. I just want to speak for a minute. Integration. So integration is generally adding up. Okay, so adding up the things is nothing but integration. So in this case, you can see normally if you have any function f of x, if this function is continuous in some interval a comma b and also differentiable in a comma b, then there exists a point C such that f dash of c is equal to f of b minus f of a by b minus a. Have you seen this? Have you seen this anywhere? Have you seen this? Yes or no? Seen this or not? You might have seen this. Okay, but this is actually the mean value of differentiation, which is normally called the Rolle's theorem. Okay, sorry, this is actually called the Lagrange's mean value theorem. This is Lagrange's mean value theorem. But anyway, here in this case, such that c first of all lies between a and b, and f of c is equal to 1 by b minus a times integral a to b f of x dx. This is actually a mean value theorem of integration. Okay, so this is actually mean value theorem of differentiation. Okay, and this is actually mean value theorem of integration. Now let's see. Anyway, this will talk at some other context, but right now why this is important is, look, I'll explain you how this happens. You can understand clearly. If this is x, if this is y, if we have some function y is equal to f of x, okay, so y is equal to f of x, then clearly one thing that you know is, if you calculate this complete area, the value of this area A is nothing but integral a to b f of x dx, correct? Which you know from simple applications of calculus, that the area under the curve is given by, like for example, say this is x is equal to a and this guy here is x is equal to b. Okay, then you can see clearly the area under this curve is given by integral a to b f of x dx. But at least at one point between a and b, if this function is continuous, okay, so this is continuous, it's a clearly closed area. Now if this is closed area, then you can identify at least one point C somewhere such that if you take this rectangle, then whatever the area you are losing here, same can be compensated here. There exists definitely one point, maybe this is f of c, okay? This line can be maybe here or at any location, but definitely there exists at least minimum one point such that whatever the area you are losing here can be compensated here, and the area under this rectangle is same as the actual area under the curve. Yes? Yes or no? Correct? We usually use that in deriving centroids of continuous bodies. Yeah, generally we'll go for in deriving centroids of bodies. Okay, so this is what we have. Okay, now whenever you have this, if both these areas are same, this area should be equal to area of the rectangle. So area of the rectangle is nothing but length b minus a into this height, which is f of c. 0 if this is 0, 0 to f of c. So that's how, if you bring this 1 by b minus a here, this is how you have f of c actually. Clear? So similarly, whenever there is a function of velocity changing with respect to time, if you want to calculate the average, okay, so such that these two integrals are same, then t into u bar should be equal to 1 by t times integral 0 to u dt. Okay, and what about u dash? U dash is called fluctuating component of velocity. Fluctuating component of velocity. Okay, so this is called fluctuating component of velocity because in this velocity there are two components. One is the time averaged value and another is the fluctuating component. The another point where you use this is actually this concept, or this concept is used in a lot of places actually, which you may not know that you are using, but actually you use it. Centroids calculations, mean temperature of heat addition, Rankine cycle, mean temperature of heat addition, okay, Rankine cycle here. You might have seen in case of Rankine cycle, whenever the heat addition is at constant pressure, mean temperature of heat addition is calculated from 2 to 3 TdS by S3 minus S2. Of course, ideally if you take pump outlet is 2 and boiler outlet is 3, then this is what you might have seen for calculating mean temperature of heat addition. This is same as the case. Okay, so normally in case of a second law analysis, since you assume heat ejection and heat addition are at constant temperatures, so you know, in case of Rankine cycles, heat ejection, condensation happens at constant temperature, but this particular heat addition is not at constant temperature, it's at constant pressure, so we actually idealize it. Okay, so anyway, these are different things. And also u dash is actually fluctuating component of velocity. Okay, so we split the velocities. I hope you have understood this. Now if I slightly move forward, just a minute. Yeah, this implies u is equal to u bar plus u dash, fluctuating component of velocity. Okay, now try to understand one thing. If I multiply this dt on all sides, u bar dt plus u dash dt, okay, and if I integrate it from 0 to t on all the sides, and if you divide it with 1 by t, now tell me one thing, over a given period of time, this u bar is a constant, so this gives you 1 by t integral 0 to t u dt is equal to 1 by t, or if you take u bar out, this is nothing but 1 by t into integral 0 to t dt plus 1 by t integral 0 to t u dash dt. This is the simple equation what you have. Okay, are you all clear till this point? Good morning. So are you all clear till this point? It is just some mathematical adjustment, that's it. I haven't done anything big. I'm just making you understand how the velocity is taken for the analysis in case of turbulent flows. That's it. Okay, clear till this point? Okay, now I hope it's clear, right? Yeah, now if it's clear, then you can have a look. Can you tell me what is this quantity here? what is this quantity? This quantity is nothing but u bar, right? So that quantity is u bar, and if you integrate this integration and this t gets cancelled, because this integration value is again capital T, integral 0 to capital T dt. If you integrate, you will get capital T. Then you have u bar is equal to u bar plus this quantity. Can I write this as u dash bar, which is mean of fluctuating component of velocity, mean of fluctuating component of velocity, fluctuating component of velocity actually. So can we say this? Now clearly these two guys gets cancelled. That means u bar dash is equal to 0. Means the mean of fluctuating component of velocity in a turbulent flow is always 0. That question was asked in GATE 2016 mechanical. Okay, they've asked the fluctuating component of velocity of the fluctuating component of velocity, the mean of a fluctuating component of velocity in a turbulent flow is dash. They have given you some options in the, it's MCQ actually. So u dash bar is equal to 0. Clear? Is this point clear to all of you? Means what is the meaning of this? If you see this profile, for example, let us say at this time, okay, for example at this time, what happens? The difference between these two, this guy is called u dash at this point. Similarly, at this point you can see this is u bar and this is the value, so this is u dash. So if, and similarly at some points you can see this is the magnitude of u dash, it is negative in this case. So if you sum up this u dash at all the points, then definitely the sum is going to be 0, like how you have the relative roughness in case of a surface finish. Clear? So please type in the chat box, is this clear to all of you till here? Okay, fine. Now let's try to understand few more things. Oh, sorry. Yeah, stresses or shear stresses in turbulent flows. Shear stresses in turbulent flows. Okay, so how do we calculate this shear stresses in turbulent flows? Okay, so first of all, what are the different shear stresses, or what are the different stresses that are present in a critical turbulent flow actually? So if you have, for example, a pipe, okay, if you have a pipe in general, now if you focus a bit on this region, okay, so anyway this is a pipe wall. Okay, so if you focus a bit on this region, slightly let the wall appear. Okay, so this region, in this region, and one thing that you know is the fluid particles inside will move in a zigzag way. Okay, the turbulence, because of the turbulence, different layers will flow in different ways, and there is certain mixing of the fluid layers also. Okay, so zigzag motion of fluid layers, Okay guys, please keep in mind these are not streamlines. Okay, they are path lines. Okay, so paths followed by different particles, they can intersect clearly. Okay, and things are highly turbulent. Now in this region, if you observe, normally let us suppose if you take a fluid particle, here, what happens? Let's say for example this fluid particle is willing to move in this direction, for example. Okay, then for the movement of this particle, there is restriction due to two causes actually. First cause, because this particle is close to the plate, because of the viscous effects of the fluid, because every fluid has certain viscosity. So because of the viscous effects of the fluid, this particle will not be able to move effectively in that direction, correct? Because the resistance to the direction or the motion of the particle depends on this viscous effects of the flow. Second point, when this particle is trying to move in this direction, maybe some other particle may come in this direction and it can obstruct the particle. Yes or no? Like for example, when this particle is trying to move in this direction, maybe some other particle, which is because of mixing, what happens? Some other particle may come and hit it and it can disturb it. So the viscous effects or the resistance to the flow of a particular particle is due to two causes. One is due to the viscous effects because of the viscosity of the fluid. Second is due to the eddiness or the mixing of the fluids. Because of the collisions, they also offer certain resistance actually. Okay, so therefore shear stresses, if you analyze this region, if you take this pipe wall, this is actually your pipe wall. Now in this case of your pipe wall, what happens is you generally divide it into 3 layers, and this is the third layer which is above this. Okay, in actual case these lengths are very small. This is called sublaminar layer, one of the most important layers actually. So this is sublaminar layer, and within this region you can see viscous effects are dominant. Viscous effects are very dominant. The reason, because of no slip, clearly the fluid layer which is at this particular point will be at a relative velocity, which is, if this is a pipe wall in general, this velocity is 0. Okay, and from 0, turbulence is actually associated with very high velocities. Particles keep on moving very highly randomly, because you also know inertia force by viscous force gives you Reynolds number, we have seen in last class. So in case of turbulent forces, even though there is certain presence of viscosity, the inertia forces are very dominating. That's why the Reynolds number of the flow is also very high. Okay, so when Reynolds number of the flow is very high, even though there is presence of the viscous plate, the fluid particles will try to move effectively, and inertia forces are very high. So what happens, within a very small gap, the particles keep attaining the velocities, and within this region, velocity gradients are very large. Okay, so when velocity gradients are very large, you know, if this is a Newtonian fluid, for example, tau W is equal to mu into dou U by dou Y. Now when these velocity gradients are very large, the shear due to this viscosity is actually large. So that's why in a region which is very close to the plate, viscous shears are pretty much dominant. Okay, and when you move far away from this viscous effects, let us say in this region, so in this region what happens, like let us say if you move little far away from this wall, here even the viscous effects are present, but compared to this viscous effects, since the layer is away from the wall, the effect of this turbulence, or basically the effect of the eddy viscosity, is generally very large as compared to the dynamic viscosity or the kinematic viscosity of the fluid actually here. Okay, so here eddies are mainly responsible for the viscosity. Okay, and a layer in between, it's like a transition. Always you never have a complete shift, so you have certain transition period. So this is the transition layer. So if you actually worry about the shear stresses in a fluid flow, this shear stresses is due to two parts. One is viscous and one is due to the eddiness. Okay, so viscous shear, and also this is due to the eddiness in the flow. Okay, now we have well defined theories for calculating this part, because we can see we have certain defined theories how to calculate the shear stress, but calculating this guy is not very simple. Even till today we don't have very extraordinary or very greatly matching results which were analytically derived. Okay, so turbulent flows is still a big area of fluid mechanics, which majority of the portion is unsolved actually. Okay, now anyway, if you talk about this, there are certain theories which came up, like these are our experimental models. Again, we have this called Bosnesque model, and we also have the Reynolds model from the 𝐂𝐚𝐴𝐻 experiment. Okay, so we have a lot of things. Finally, what we do is we generally use this Reynolds model, and we try to analyze this as rho times u bar dash v bar dash actually. Okay, this u bar dash and v bar dash are the fluctuating components. Again, in case of normally these values should be large actually. Okay, and you will, sorry, this is not individual product, this is u dash v dash bar. Okay, so this is the average product. Okay, not the individual product, because individually, you know, they are going to be zeros. So u dash v dash bar is what we actually take. Okay, so this is completely empirical. This relation is based on this particular models, and we calculate that models from something called 𝐂𝐴𝐻 experiment, which in a course I'll show you maybe. So this is called 𝐂𝐴𝐻 experiment. Maybe I will have a slide, I'll show you. Okay, I'll show you the notes which could be helpful to us. Yeah, just a minute, I'll bring a quick sort here. So turbulent flows 1. Yeah, so here it is. Okay, so you can actually see all these things. So you can see this is viscous shear, and obviously one is due to eddiness, which is the turbulent shear, and this anything I have showed you. So now, oh sorry, let's slightly reduce it. I hope you can see this. Okay, So in case of this turbulent flow, so if you see a region about y, so this is basically the sublaminar region where the viscous effects or the viscous shear is actually predominant. Okay, and if you move away, because of the reasons I told you, this is called outer turbulent region, and normally this turbulent shear is predominant in this case. Okay, and this is actually a overlap. Okay, so basically the transition layer from where this viscous shear stress is becoming dominant to this eddy shears or turbulent shears becoming dominant. Now anyway, you can see in case of this turbulent shear, so tau is summation of these two parts. For viscous shears, we know how we can calculate, but for the case of this models, you can see lot of Bose-Nash model, all these things we have discussed in detail, but again all these are again based on only the complete based on only the complete experimentation results and empirical fits actually. Okay, so for this Reynolds turbulence model, you can see this is what we actually assume for the modeling of this tau E actually. Okay, now finally what I want to tell you is, after a bit of simplifying analysis, there is certain concept called the Prandtl's mixing length, L mixing length. So what is this Prandtl's mixing length? I'll just give you in a brief. Let us say there are two layers of fluid, adjacent layers of fluid, for example. Okay, so there are two adjacent layers of fluids like this. Okay, so these are two adjacent layers. Now because of the collision, this particle will travel to somewhere here, but the distance traveled in the direction opposite to the flow or normal to the flow, you can say the direction normal to the flow is called this Prandtl mixing length. But during the shifting from here to here, one thing that should remain changed is momentum of the particle should be conserved. Momentum of the particle should be conserved. Momentum of the particle should be conserved actually here. Okay, so sorry, please explain sir, u dash v dash part. Yeah, it's purely empirical part. You can see in this case I have shown you. Look, here I'll have this tau is actually combination of these two. I hope this part is clear. So for calculating viscous shears using Newton's law of viscosity, we'll calculate this. But coming to this Reynolds model actually. So in case of this Reynolds model, what we do is we tau t average is taken as rho into u dash v dash. Basically what happens, like how I have taken as u dash as fluctuating component of velocity in x direction, fluctuating component of velocity in x direction, Similarly, this v dash is nothing but fluctuating component in y direction. Now the product of these two at any point and the mean of these two together is what we'll use in the modeling of this particular quantity. Okay, and normally if you do scaling, you will come to know the magnitude of this term will be approximately this. That's why it's not like, since there is a bar I can split individually, it's not mathematically, but it is normally due to the scaling part which you can split this. Okay, normally you cannot say xy bar is equal to x bar into y bar mathematically. Okay, but if you compare the magnitudes, they'll be comparable in this particular case, and this is again based on this responsible for ediness, and this is based on this model which is given by Reynolds again. Okay, so using this model and this concept of Prandtl mixing length theory, you can see there is a certain detailed discussion from the 𝐂𝐤𝐧𝐤𝐬 experiment. This case called 𝐂𝐤𝐴𝐻 constant, actually 0.4 is the value of 𝐂𝐤𝐴𝐻 constant. So after doing a bit of things, you will come to know when you substitute that this is the transition anyway. So you can see after simplifying the things, you will end up with the velocity, identifying this velocity in a pipeline as logarithmic. Okay, so you can see after a bit of analysis, you will find out the velocity profile in a pipe, the velocity profile of fluid flow, of turbulent fluid flow, you can say, of turbulent flow in a pipe. In a pipe is logarithmic. I'll just show you how this happens because we have these notes luckily. So see here, I'll just explain you how this comes. Let's go quickly. Okay, so that's anyway the boundary layer. Someone has asked doubt at that point. Now this u dash and v dash bar scalings. Okay, so this u dash and v dash bar scalings, if you do, you will get this as from this 𝐂𝐤𝐴𝐻 experiment, from this 𝐂𝐤𝐴𝐻 constant. This u dash bar can be written as L into du by dy, and these two are equal in magnitude. Normally a bit of scaling analysis is what you have to do. So if you do, you will get the expression for the shear stress due to ediness or due to turbulent is rho times ky whole square into du by dy whole square. Okay, so then when you keep that equation, here, and if you do a bit of dimensionalization, what you'll get is root TT by O. This component is called the wall shear stress, which we might have talked later. U star it's called. Yeah, so you can see this is called U star and root of tau naught divided by rho in this case. Okay, and defining this as U star, this is a differential equation. Now if you start integrating it and doing things, you will end up the velocity profile in a pipe turns out to be logarithmic. Okay, so this depends on ln r by y, because all this is again based on this 𝐂𝐿𝐴𝐻 experiment, and some solving of mathematical equations is also there. So if you solve, you will end up with this particular equation, which is the logarithmic velocity profile in a pipe. Okay, and if you see the profiles, I might have drawn somewhere definitely. Yeah, here you can see this is the shear stress, this is the velocity profile in case of a turbulent flows. Okay, so this is the velocity variation in this case. Okay, so anyway, if you see, there is a small correction which I would like to explain you in this. So whenever there is a pipe flow, actually like this, apart from the small layer which is very close to this pipe wall, so this is actually a very small layer which is close to the pipe wall. If you take a section of particles here, the velocity profile will be logarithmic. Okay, so this profile for this part will be logarithmic. So this is logarithmic. But at the same section, if you take the particles which are close to the pipe wall, actually, okay, so if you see the particles which are close to the pipe wall, look here, the velocity is slightly, it's not 0. Just a minute, it is not a 0. We shouldn't make it 0. Actually, some velocity is there by that time already because it's not wall. So within this small layer of fluid, if you carefully observe, this variation will be linear. Okay, so this small variation in the sublaminar region is linear. The velocity profile is linear in sublaminar layer. This is also one year gate question. So this is in sublaminar layer, it is linear, and in the outer turbulent region, means basically in the towards the center of the pipe, the velocity profile is actually logarithmic. And if you calculate the shear stress variations, which I can again show you here, finally this turns out to be linear. The case will be same like the case of a pipe flow, but actually we have a logarithmic and also linear profiles in the small portions of the nearness to the boundaries actually. Okay, so right now anyway, I'm not doing the derivation and all, but just trying to give you certain small insights. Is this clear to all of you? Okay, so is this clear to each and everyone? Now everything remains same, like the calculation of the friction factors. Normally you might have seen in gate questions and all, for friction factor, friction factor is actually some function of Reynolds number. So they'll give you some expressions like 0.002 plus 0.35 divided by Reynolds number per 1 by 5. They might have given you might have seen expressions like this actually. Okay, so anything for any pipe flow, you know how to calculate Reynolds number. So if you substitute Reynolds number, then you can, in that function, whatever they give you, because all these relations are empirically generated. So in whatever the expression they give you, you keep the formula, you keep the Reynolds number value and simplify. Finally you will end up with the friction factor. So once you know friction factor, you know how to calculate losses, FLV square by 2GD, all these things you have. Okay, the only thing is I'm not showing how it is logarithmic, because you have to go through certain sequence of things for showing that is logarithmic, which is actually here in this case I have done normally. Okay, so it's not very complicated, but just time taking, and of course majority of the points which we have to take for granted because of this being experimental results. Like for example, this 𝐂𝐚𝐴𝐻 constant 0.4. okay, so you can see this 𝐂𝐚𝐴𝐻 constant 0.4, we cannot derive it actually. Okay, but it is present in many of the books actually, like you can look at Parakaram or any standard textbooks of fluid mechanics, you can find theory about all these things. Okay, and last class somebody was asking me which book to follow. Generally, one thing that I would like to suggest you is, for any fluid mechanics, always try to solve problems from unsolved questions of Frank-M-White. Unsolved questions of Frank-M-White. Okay, this is really one very good book where majority of the gate kind of questions are present. Okay, so you can get, in the sense they are very conceptual questions again. So if you try to solve them, you can have a lot of things. Okay, and also normally the practice questions in other batches and all, whatever we have solved, all these questions are from Frank-M-White. Unsolved questions majority Frank-M-White, Munson, 𝐂𝐚𝐿, these are the, and also 𝐂𝐾 Soams's book. So We have taken some good questions from them again. Okay, so anyway, this is a quick about turbulence, and we'll now start talking about the turbo machines actually, which is, in our case, we'll talk only about turbines. Okay, so turbo machines. Normally in this class we can see a lot of things are there: turbines, then pumps, compressors, okay, so fans, you have blowers, everything, a lot of turbo machinery stuff is there. But in this particular class we will look only in the turbines, because that's only in the syllabus. Okay, now if you see, what is this Euler's equation? Okay, now let me ask you something. See here, if you have, for example, a disk like this. Okay, so let's say there is a disk and there's a certain axis of the disk. Okay, so there is a disk like this. Now whenever there is a disk like this, tell me one thing. Normally in real case we have velocity as VR ER cap plus V theta E theta cap plus VZ EZ cap actually here. Means if you take any velocity vector, like how you can split it in x, y, z coordinates in Cartesian, similarly in case of polar you can split it into r, theta and z components. Okay, now let me talk to you with the help of an example. For example, let's take this bottle. Okay, now let us say, for example, if to open this bottle I have to open this cap. Okay, so I'm coming a bit close, you can see. So if I want to open this cap, then if this is the axis, for example, okay, so if this is the axis of the cap, then definitely if I have radial, axial and also tangential components of velocity, see, axial component of velocity will be located or will be oriented along the axis of the block, correct? And radial will be along the radius and tangential will be along the tangent. Now out of these three velocities, can you tell me which component of velocity is responsible for the rotation of this block? Look, if I apply a velocity axially onto this cap, will this cap rotate? So please type in the chat box. If I apply, because of my axial component of velocity, will this cap rotate? It won't rotate, right? Similarly, because of the radial component of velocity also, it don't produce any rotation. But the tangential component of velocity, let us say if I have certain tangential component of velocity, then definitely it can make this cap rotate. Okay, so that's why for rotation of any circular disc or in general any rotor, this tangential component of velocity is actually a bit important. Okay, and tangential component of velocities normally is we denote with VW, tangential, or sometimes this is also called, this W is due to the rotation, which is called will component of velocity. Okay, so this is actually the will component of velocity, and we also have the axial component of velocities. So we have axial component of velocity. Okay, so this is the axial component of velocity. Now clearly you can understand, if you want to rotate this disk, for example, if you take this as your z-axis, then some torque should be applied by the fluid on this rotor. For example, if this is a disk, for example, some small rotor or disk, you can say, then clearly the fluid, when it's coming and going, because of the change in angular momentum, it should be able to apply some torque about this z-axis. Only in that case the fluid will be able to rotate this wheel. Yes or no? Simple fundamentals. Okay, so start applying from simple fundamentals, you will easily get this. Okay, so this is actually a torque T which is applied. Now if this is torque T, then as per your Reynolds transport theorem, RTT, what we have written for angular momentum, so B is equal to, if B is equal to mass times R bar cross V bar, okay, and this beta is per unit mass. We have seen already RTT in control volume analysis and all. So if you apply the Reynolds transport theorem, we can see d by dt of m dot, let us take for example in general, okay, so for mass flow rate, m dot R bar cross V bar, this is relative of course, is equal to dou by dou t of integral over the complete control volume beta times rho dv plus integral over the control surface rho times this rho beta times here, again here we have the beta times, so R bar cross V R bar into rho dv is what you have, correct? Rho dv and cap, okay, so it's not dv, it is surface integral, so V rho V R bar dot n cap ds. So this is actually the Reynolds transport theorem what we have seen, okay, because it's beta into mass flow rate, elemental mass flow rate is what we have. Now clearly if you take any turbo machine, for example if you take a turbine, then clearly these are industrial devices and they should operate under steady state conditions. The reason for that is, see, why I'll tell you. Let us suppose if this is a turbine, for example turbine, then when the industries are continuously getting operated and all these devices inside the industries are operated, if this is m dot in and clearly if this is m dot out, then definitely these two should be equal, yes or no, because this device has to be in continuous operation. If this device has to be in continuous operation, this m dot in is continuous and m dot out is also continuous. This physically has only some particular finite amount of volume, so what the fluid, that device cannot keep on holding the fluid as long as the fluid comes out, okay. So therefore what we do, if this is m dot out and if this is m dot in, then generally this m dot in and m dot out should be equal, yes or no, because if some fluid starts settling inside, then very soon this device will get blocked, clear. So that's why this two should be equal. And similarly in terms of energy, right now here we are doing only adiabatic case, but in case even if there is some heat transfer, there should be energy balance, otherwise the temperature of this device keeps on increasing and at very soon it will reach the metallurgical limit and the material will fail, okay. So because of these reasons, the devices has to operate under steady state, okay. So under steady state, clearly this quantity is 0, okay. So it's a partial derivative with respect to time, so clearly that quantity is 0. Now if you see this, I have already explained you, this is the small elemental mass dm dot. So if you see carefully, this quantity, rate of change of angular momentum, is nothing but netted torque which is acting. So netted torque acting on fluid, because this is the momentum changes of fluids is what we are writing. So angular moment, this completely gives you, I have explained you, if you have some finite number of inputs and outputs, this is nothing but summation of m dot r bar cross v r bar at the outlet minus summation m dot cross r bar cross v r bar at the inlet. So this is what even I have told you in control volume analysis in these lectures. So is this clear? Now let's understand one thing. If you have this particular expression, then this is net torque acting on fluid. In case of turbines, what happens is, okay fine, so let's say this is net torque acting on fluid. So in z direction, because about z axis, okay, about z axis, if you take the z component exclusively about z axis, because the rotation will happen only because of the torque acting about z axis. If it's acting about radial or theta axis, then definitely the blade will twist or the rotor will twist, okay, which is not required for us. So in order, and also the blades are very strong, normally this don't happen whenever the fluid actually comes. The main reasons of failure of turbines and all in industries, if you see carefully, it's not due to the bending of the blades and all the things, okay. Normally cavitation is one issue where majority of the blades get damaged, and also erosion, blade erosion is one major problem, okay, in industries. Normally if you see eroded pumps and all, since we are using this, let's take some advantage. So eroded pump, you won't even imagine to what levels pumps gets eroded, okay. Normally I have seen many in HPCL when I was working, but yeah, this is a good example. First of all, you can see this is actually the picture of a pump which got damaged here. So yeah, now it's better, I think, the resolution. Now you can see that to the level at which the pump gets eroded inside, okay, because normally let's suppose if you are sending some oil or diesel, petrol, or maybe even in case of water pumps, what happens because of the impurities and all, it gets damaged severely, which you are able to see inside, okay. So there is a lot of erosion. Similarly on water blades, if there is some erosion on the water blade, which I can show you, this is a blade actually, you can see it got eroded so much in this case. This is again one of the eroded pumps. So you can see even at small places, because of the high impact of the water particles, they could even, after eventual eroding of the material, they could even create some block holes also, okay, which is not very desirable. So anyway, now if you see about z axis, the torque acting for the rotation by fluid is nothing but, if you resolve this cross product in the z direction, you will get m dot into v relative, but that's again vw into r at outlet minus m dot vw into r at the inlet. So this is called Euler's equation normally, which you generally see here. So this is your Euler's equation. Euler's equation, because this is the component of velocity which is responsible for the change in torque of the fluid. And also you can see, if this is by fluid, then clearly torque acting on rotor is equal to m dot v relative or vw, you can say vw into r at inlet minus m dot vw into r at outlet, because this is on the outer. Okay, this is on fluid, this is this is on fluid, right? Yeah, this is on fluid, we have written on fluid here. So this is outlet. Okay, so this is on fluid. So if this is on fluid, then definitely on the outer just a negative of that. Okay, sign will be changing. Scaling on blade cavitation, yeah, all these are scalings will happen because of this impurities and all. Normally you might have seen fouling is also one of the main reasons actually. Okay, because whenever impurities come, you know, in thermodynamics you might have studied in heat exchangers exclusively, whenever we have a pipeline or any device, the scales starts forming on that particular body. Okay, so anyway, there are a lot of ways in which a machine can fail. Metallurgical failures are predominant, and also mechanical failures because of the mechanical erosion of the blade materials. All these things are responsible. Okay, so anyway, if you come here, so m dot vw r in minus m dot vw r out. So this is the Euler's equation, and this talks about the torque which is delivered to the rotor actually. So is this clear to all of you? So please type in the chat box. Is this clear to each and every one of you? Okay, fine. Very much, and physics, 𝐂𝐸𝐬, all of you. Okay, now let's understand certain things here. In case of turbines, actually, you can understand one thing. T on rotor should be positive in general. Okay, normally this has to be positive because the torque which is subjected to the fluid by the fluid on the rotor has to be positive. Now when the torque submitted by the fluid on the rotor has to be positive, out of these two guys you generally try to maintain R inlet greater than R outlet actually in this case. Okay, so normally I think I have shown you at some location also. Normally in case of Francis wheel, in all these cases the fluid will enter into the turbine at higher radius. This is not generally for impulse turbines. In impulse machines the fluid enters and comes out at same radius in general, but in case of reaction machines exclusively, that too exclusively in case of radial machines, this radial fluid inlet at the radius is generally high as compared to the fluid outlet radius. Okay, so anyway, we'll see these things in detail in a bit of time. First of all, I want to make you understand certain things before we go forward from here. We would like to talk about something called velocity triangles. Velocity triangles. Now let's see, for example, you have a blade. Okay, first of all I would like to give you some idea. So see here, let's say this is axis, for example. Okay, and you have a set of, you have a turbine, for example, like this. Okay, let's say it is vertical axis. Then clearly you have lot of blades here, and the turbine, if it's rotating at any particular point, the blade will actually move in this direction. Yes or no? Correct? Normally, see carefully here. What happens whenever the axis is like this, and let's say for example if I have a bottle cap. Okay, so for example if I have this, and every time I get confused in this part. Look, अभी मैं आपका सारा confusion दूर करता हूँ. देखिए, let us suppose if we have this, for example, if my wrist is actually rotating in this direction, okay, about this axis, and let us say all my fingers are blades, for example. Okay, so whenever my fingers are rotating in this direction, depending upon the radius of different blades from my particular shaft, we have V is equal to R omega. So everywhere the particles will rotate. Now clearly one thing you can understand, for the rotation of these blades, some fluid which is having the velocity component, this is the tangential direction. Okay, so this is the tangential direction in this case. So when some fluid go and hit the blade, then definitely this will rotate about this axis. Is this clear to all of you till this point? I'm telling, this is the tangential direction and this is the axial direction. So clearly whenever some fluid particles will come and hit, these blades will actually rotate at certain velocity u, which you call normally the blade velocity. So this is how the rotor actually rotates. Is this clear to all? Yes or no? So type in the chat box. Is this clear? Means the fluid may not exactly enter like this, it may enter somewhere like this, but this component of velocity which is in this direction is actually responsible for the rotation. Okay, I'm not saying the fluid completely moves in this direction. Maybe fluid can move in any direction depending on the inlet to the turbines and also. Let's say for example if fluid is moving in this direction, but out of this complete velocity, the velocity which is acting in this direction is responsible for the rotation of the rotor. Clear? If you have any doubts, please ask me till this point. Is everything clear? Okay, now let us see. So this is the tangential component clearly, and this is the axial component which you call VF generally. Okay, and blade velocity is in this direction. U is the blade velocity. Okay, now if you take the velocity triangles, if I take one blade and if I draw the triangle, let's see how it comes out. Let's say for example this is the blade what you have. Okay, if this is the blade, it need not be symmetric. Okay, you have a blade. Now clearly this blade is actually moving with certain velocity which is u. Okay, u is called blade velocity. Blade velocity. Okay, now whenever this u is blade velocity, if you talk about this is the fluid jet, like for example it can come at any angle. So if this is your fluid jet v1 velocity vector and this is coming at an angle of alpha 1. Now tell me one thing, do you really feel if this fluid jet is coming at a velocity v1 and this blade is also moving in this direction, so this edge will also keep moving. So clearly this v1 at an angle of alpha 1 will not clearly reach this jet, or it cannot enter the fluid, it cannot enter the blade actually. Okay, so what we do, we know relative triangles or relative velocity. When the fluid is actually traveling in this direction, this u if you bring here, so this is actually the blade velocity u, which is in this case. So if this is u, then clearly the relative velocity between these two is given by this. So the relative velocity is given by this actually here. Okay, so this is VR1 which is relative, and clearly when you write relative velocities, absolute velocity is equal to relative velocity plus the difference, which is nothing but this blade velocity in this case. So this is u bar actually. So this is the simple normal velocity triangle. You can see vector addition. This is u. Why I have written u in this fashion? Because the blade is moving in this direction. Okay, so this is u. So u is here, v1 is here. So the relative due to these two is actually vr1, which is coming in this way. Got it? Yes or no? So please type in the chat box. Okay, now let's try to understand some more things. So clearly if you resolve this v1 into two parts, this component which is actually in the movement of the direction of the blade is called the tangential velocity, which is, or the wheel velocity, which is responsible for the rotation, and this is the axial component of velocity, which is vf1. You might have seen these things in your velocity triangles actually. So if you resolve this, you can see clearly this v1, if you resolve, it has two components, which is vw1 and also vf1 in this case. Clear? Yes or no? So please type in the chat box. Okay, all of you. So please type in the chat box. Clear to each and everyone? Right? Normally if you call this alpha 1, you sometimes call this angle beta 1, which is the relative angle at inlet. Okay, fluid velocity, relative angle at which fluid enters the blades. Similarly, if you draw the same story at outlet, you can understand the blade, the fluid actually comes out along the blade. Okay, so this is V relative because it comes out along the blade, VR2 at an angle, blade outlet angle. Normally if you take beta 2, okay, so this is beta 2, so this is the angle at which it comes out. But the absolute velocity at which fluid is coming out is something different. For getting that, you know, you should have this u, the same u which is here, this is again u, okay, and this is u bar. For example, if this is VR2 bar, then clearly the absolute is vector summation. So the vector sum is from this point, we can take this color maybe, and you can say the vector sum is this. This is the closing vector, which is v2 here. And clearly, if you resolve this v2, you can see this is again the axial component at the outlet and at the inlet. Okay, so then this is your vw2 and this is your vf2 if you resolve into two components. That's it. Okay, so this is vf2 which is acting in this direction. Clearly, if this is the resultant of these two, then you know you have this as the velocity vector. Okay, so vf2 and also vw2. Clear? It's just a vector resolution. You know, if like for example, you know, if the resultant is in this direction, then these are the components. That's it. Okay, nothing very complicated about this. Clear? So similarly, this v2 is also responsible for vr2 plus u actually. Okay, which you can see from the vector summation, vr2 plus u2 will be in the closing direction, which is v2, and u plus vr1 which is in the closing direction, which is v1 from that triangle. Okay, now if these are the velocity triangles, so before going for certain things, I want to make you understand few things here. So m dot vw are at the inlet minus m dot vw are at the outlet. So if you take that expression, this gives you torque on rotor is equal to m dot is same because you know steady state. So at inlet and outlet, if you have a single inlet and single outlet for a blade, so clearly this summation can be eliminated, only one inlet and one outlet if you take, then this m dot is same at both the locations. So if I take them common, then vw in at the inlet, what you can do, this product vw into r at inlet, since inlet conditions we are denoting with 1 and outlet notations we are denoting with 2, what you can write, vw1 u1 sorry r1 minus vw1 sorry vw2 r2 is what you have here. Okay, so this is what you have, vw2 r2. So this is the final answer that you have. So this is the energy delivered or the torque delivered to the rotor by the fluid. Now normally, more than torque, we are interested in power. What is the power that is generated by the things? So before going for efficiencies, let us try to understand what is power delivered by the fluid to the rotor actually. Okay, so now let us say this turbine is rotating at an angular speed of omega. Let turbine rotate at omega speed, for example. Okay, so let us say this turbine is rotating at an angular speed of omega. Then power delivered to the rotor, power delivered to the rotor actually is equal to P, which is energy to rotor, energy on rotor delivered is equal to, you can see omega. So power is equal to torque into omega, you know this. Okay, torque into omega is the power. In linear mechanics you can see, sorry, in rotational mechanics. So this is m dot into, we can say vw1 r1 omega minus vw2 r2 omega. Can I say this, yes or no? So please type in the chat box, can I say this? Can we say that vw1 r1 omega minus vw2 r2 omega? Now clearly r1 omega is nothing but radial velocity of the inlet of the blade, and r2 omega is the velocity at the outlet of the blade. So you can say r1 omega is equal to u1, which is blade velocity at inlet, blade velocity at inlet, and r2 omega, which is u2, which is blade velocity at outlet. Like you can see, for example, if there is a shaft like this and if there is a blade which is attached like this, then clearly this point and this point will be at different radius in case of machines. Okay, so let's say if this is the axis about which this complete turbine is rotating, then clearly if this is r1 where the fluid is coming like this, and if it's leaving somewhere, okay, normally r1 will be larger than r2. So let's say if it is coming and it's leaving like this, then this is r2 and this is r1, then clearly here it's u1 and here it's u2. The velocities can be different. Okay, but generally in case of Pelton wheel, in case of certain impulse machines, where the fluid generally makes impact at one particular point and comes out at same radius, we don't think much about these things, but actually they are important. Clear? Did you understand? Let's say there is a blade like this, and if the shaft is completely rotating about this, then clearly when the fluid enters at u1 and if it leaves at r2, depending on this r1 and r2, this complete rotational speed is omega, then this linear velocity is u1 and this is u2 actually in the tangential directions. Clear? Yes or no? So please type in the chat box. Here you are seeing radial and theta. Okay, that's it. Radial and z direction, sorry. So theta is in this direction. Is this point understandable to all? Can you all understand that this R1 omega and R2 omega we can write as U1 and U2, blade velocity at the inlet of the fluid and blade velocity at the outlet of the fluid. Yes, clear? Then let's, anyway, I'll keep this for, okay, this is anyway, it's fine. Now you can understand something, see. So anyway, this is an extensive quantity depending on discharge. So first of all, you can replace this quantity with U1, blade velocity at inlet, and blade velocity at outlet, clearly, okay. And see, energy delivered or power delivered to water, power delivered to water by unit weight of fluid, unit weight of fluid, by unit weight of fluid, which means it's nothing but P by m dot into G actually, okay, because this is the unit weight per second which is flowing into the machine. So you call this H because this has the dimensions of H, clearly head. So this we call it H. So this can be written as m dot times VW1 U1 minus VW2 U2 divided by m dot into G actually, okay. So this is what you get, m dot if it gets cancelled. So the head delivered to the water by the fluid is actually what you have as m dot G. So here all velocities are 2D vectors. Yes, because we are not taking anything in radial direction. Okay, that's what. We are not considering any radial variations. That's what. Okay. Here we are mentioning in terms of 2D vectors only in the, you can see the velocity triangles. We have only the tangential and the axial components because we are not focusing anything on the radial part as of now. Okay. Normally in gauge syllabus you don't have any radial variation. Because whenever you have a blade, what happens when fluid travels, when radius of the fluid particles changes, the angular momentum, everything will change. But whenever you are telling radius at inlet, radius at outlet, that means we are locking at a particular location. Okay. Like for example, I'll tell you, in case of a Pelton wheel, you can, I can explain you with simple example. Maybe I understand slightly 3D because all this is 3D picture. So Pelton wheel, if you see images, I'll show you. We'll select one good Pelton wheel. Okay, so this is a fantastic Pelton wheel. Yeah, let's take this for example. Okay, so let's take this first example. Yeah, I think you can see the Pelton wheel. Okay, now let us see if this is the axis. Okay, see this figure carefully, you can understand. This is the shaft and this is the rotor which is mounted on the shaft, it rotates. Okay, and this is the tangential direction clearly. Now let us suppose if you put a if you put for example a nozzle here. Okay, and if this nozzle is hitting these blades, try to understand one thing very carefully here. Let us suppose if the nozzle is here, it can hit the fluid at this radius, at this radius, or at this radius. At different radius it can impact. Okay, but different fluid particles will actually impact at different radial locations, because compared to this shaft, means when you start measuring from the center of the shaft, all these particles or all these points on this bucket are at different radius. Okay, so but right now we are not considering this. We are considering only the tangential component and also the axial components, and we are talking the variations. We are not considering the variations of the fluid particles with respect to the radial distance on the blade. Clear? Okay, did you understand why we are not taking a radial velocity components in this case? Because we are assuming that the complete fluid particles are going in at one particular radius and coming out at another particular radius. Okay, so anyway, this is what you have. Therefore, head delivered to the rotor is H is equal to VW1 U1 minus VW2 U2 by G. Okay, so this is what you have. Now normally if you look at a triangle, or basically if you look at things, identifying this VW1 is not very straight away. You have to do certain mathematical analysis from the turbines. Okay, now let us see what you can do. See here, for getting this product VW1 U1, you know V1 is equal to VR1 plus U. Okay, or you can also say VR1 or V1 is equal to VR1 is equal to VR1 is equal to V1, because V1 you can measure directly, U also you can measure directly. Okay, so V1 minus U. Now try to understand one thing. If you do want to calculate the magnitude of any of these vectors, like what you do, you will do the dot product of the vector with the same vector and take a square root. Okay, like for example, let us say there is a vector A bar. Okay, and if I want to know what is the magnitude of this vector, how do I do? Normally I'll do a dot product with the same vector and then take a square root. This will give me what is the magnitude of this vector. Similarly here, whenever there is a VW1 U1, since VW1 is not directly calculatable, we have to do something to convert this VW1 in terms of these quantities, because these are directly known quantities. Okay, so let's see what we can do. If you do the dot product with VR1, this actually gives you, okay, so V1 minus U1, V minus U dot V minus V1 minus U is what we have. Okay, now if you do the dot product, it's very simple. This is anyhow VR1 square, because this is now a scalar. Dot product of these two is a scalar, and that's nothing but magnitude of VR1 whole square. Okay, magnitude of VR1 whole square, and V1 dotted with V1 gives you V1 square, plus V1 dotted with U gives you minus V1 dot U. Again, minus U dot with V1 again gives you minus V1 dot U, or U dot V1. Dot product is commutative, we can write any dot product. Minus of minus plus U dot U gives magnitude of U square. Okay, so this is U square, actually 1, of course we have 1s here, so this is U1 1 1 square. Okay, so this is U1 square. Now try to understand what we can do to this dot product. This expression is nothing but V1 square plus U1 square minus 2 times of V1 dot U1 actually. Okay, now you can see this can be written as V1 square plus U1 square minus this can be written as 2 V1 U1 cos, what is the angle between these two, V and U? See, this is V1 vector and this is U vector, so you can take this as alpha 1. Okay, so if this is alpha 1 blade inlet angle, alpha 1 is the blade inlet angle here in this case. So if this is blade inlet angle, then can you understand one thing? If you expand this dot product, you will get V1 U1 cos alpha. So I am writing that as 2 U1 into V1 cos alpha. Can I write this? Yes or no? For compressible flow devices, does the intuition is same for velocity triangle like gas flow turbines and compressors? Normally it's not. Okay, there are slight changes, depends on the compressibility effects, because when I'm writing this VU, all these things, one important assumption that we make is no density variations. Okay, otherwise the steady flow equation, we have taken this m dot out here. Okay, m dot out, and we have cancelled, but there we can see we get the expressions in terms of this velocity and density, velocity and density, which creates certain variation. Okay, so that's why normally in case of gas turbines and all, the analysis slightly changes for the velocity triangles. Okay, normally at BTech level and in the gate examination level, you do the maximum velocity triangles only for the steam turbines. For gas turbines, if you take the compressible effects, okay, things actually change. That's how actually your Rayleigh flow and also Fano flows, all these things comes into picture. Normally when not only in hydraulic machines, normally if you take any turbines and nozzles, okay, flows in a nozzle and all, if you analyze, the flows change actually. Clear? Okay. Fine, shall I continue? Is this clear? Now when you do this dot product, now can anyone tell me what is this particular V1 cos alpha from this velocity triangle? What is V1 cos alpha? What is this V1 cos alpha? V1 is actually the magnitude of this V1. V1 cos alpha gives you something. What is that? It's nothing but VW1, correct? So this is VW1. So clearly you can say this quantity is nothing but your VW1. So this implies, if you see carefully, this VW1 U1 or VR1 square is equal to V1 square plus U1 square minus 2 U1 VW1. So therefore your VW1 U1, the tangential component of this conversion, will give you something like V1 square plus U1 square minus VR1 square divided by 2 is what you will get from this particular triangles. Okay, so this is the velocity triangle which actually gives you this VW1. Okay, so if that's VW1, then you can write here, this implies H is equal to then V1 square plus U1 square minus VR1 square by 2. Similarly, if you do for the other triangle, what you will get is V2 square plus U2 square minus VR2 square divided by 2, and this G is also there, so G is here. Okay, so this is what you get. Now if you calculate this, V1 square minus V2 square by 2Z plus U1 square minus U2 square by 2Z plus VR2 square. Here you should be careful because this minus of minus gives you plus for this and minus for this because of this. Okay, so minus VR1 square by 2Z. So this is the total head which is actually brought. Now one thing you can understand, normally this V1 is direct change in fluid velocity. Okay, like for example, you see fluid is coming in V1, it's leaving at V2, so definitely it's expected that the energy, kinetic energy change of the fluid should be submitted as should have done some work actually. Okay, so the kinetic energy change of the fluid, which is actually V1 square by 2 minus V2 square by 2, of course per unit weight and all. So that is the direct energy supplied. But how these extra terms are coming? These two terms are coming because of the pressure analysis, because right now we are not considering viscosity. The total energy of the fluid, or what is the energy difference in the fluid, that should be equal to work done. So clearly this is the head supplied. So that if this is the head supplied, this part is directly due to change in dynamic head. Because clearly the fluid velocity is changing, so definitely this part would have got converted to work. Fine, 100% agreed. But this part is also there, okay, and this part do not correspond to any direct change in kinetic velocity. So this velocity change is due to the pressure difference actually. Okay, so this part of energy is done because of change in static pressure head, or sometimes you simply call it change in static head. That's it. Okay, so this is due to the change in pressure, because finally the complete, if you see the Bernoulli's equation, P by OG plus V square by 2G if you neglect any potential effects. So the difference in this energy of the fluid between inlet and outlet must be equal to the work done, correct? So that's what these terms imply. This is change in dynamic fluid, change in dynamic head actually. So change in dynamic head, which is actually directly due to the kinetic changes, and this is change in static pressure head actually. Is this points clear to all of you? Yes or no? Okay, so is this clear to each and every one of you? Did you understand? Like if you take the Bernoulli's equation, what I'm telling you is, I'll maybe give you a short insight. P by OZ plus V1 square by 2Z is equal to minus, this is the energy at the inlet, minus per unit weight P2 by OZ plus V2 square by 2Z. This difference should be equal to some work done per unit, per unit weight of the fluid. So this is capital H. Now clearly you can see this term V1 square minus V2 square by 2Z here. Okay, so clearly this can be seen, but this part is due to P1 minus P2 by OG actually. Okay, so that part of the complete energy supplied belongs to the static head. Now sometimes what happens, let us suppose if the inlet to the fluid and outlet to the fluid both are actually open to atmosphere, for example, so P1 and P2 are same, then clearly this term will be 0, because in that case U1 will be equal to whatever happens, this complete summation will actually go to 0. So normally in case of impulse and reaction machines, how do we classify impulse and reaction machines is basically, in case of impulse machines, change in static head is straight away 0. Means whatever the energy available at the fluid entry, the complete energy is available in the form of a only kinetic energy. Okay, no pressure energy is available at the inlet to the rotor actually. So similarly when it comes out, nothing changes, so pressure energy remains same total all over the rotor. By the look, let us suppose if you take the rotor as a, for example, some chamber, by the time fluid enters, whatever the pressure energy is with the fluid, the same thing will be available when it comes out, and this change in static head is actually 0 for impulse machines. That's why the name is also impulse. So whatever is the power generated, that is only because of the impulse impact of the fluid, nothing due to the change in pressure actually. Clear? And in case of reaction turbines, reaction change in static head is also available, is also change in is non-zero, you can say, for example, is non-zero. The meaning of this is, when nothing is actually changing in terms of static head, the energy available at the rotor, energy available at a rotor inlet, is only due to kinetic, which is the dynamic head, is only kinetic energy. Here kinetic energy will be obviously there, plus along with that you also have pressure energy, because of which the wheel will actually rotate. See in these things, You might have studied the same thing in a different way, that in case of impulse machines only kinetic energy is available, in case of reaction machines kinetic plus this pressure energy is also available. You might have studied in books as different things, but the reason is when you analyze these velocity triangles and little understanding of Bernoulli's equation, you will come to know this is directly due to the dynamic head impact, but this term is due to the pressure energy change. Clear? Okay, so please type in the chat box. Yeah, tak sabko clear hai? Yes or no? Please type. Come on guys, quick, be fast. We have to cover a lot of things again. Okay, clear? So I'm moving forward then. Now there is one important term which actually quantifies the impact, the effect of this reaction. There is something called degree of reaction. Degree of reaction, which is normally denoted with R. This tells you the effectiveness, how well pressure can be utilized, because kinetic energy is look, when out of these two energies, kinetic energy is a direct impact. Okay, so normally by simple calculation you can clear answer. Good. Okay, so but in a machine, normally what does a good hydraulic machine able to do? A good hydraulic machine will be of that machine where out of the total energy coming onto the water should try to grasp a majority of the energy from the fluid, correct? So degree of reaction is one such measures of performance of the machines, where out of the complete pressure energy available, how much pressure energy can be utilized by the machine in converting it into power. Okay, so anyway, this degree of reaction R is defined as change in pressure energy, or basically change in static pressure head across the turbine water, change in static pressure head across the water divided by this quantity divided by change in total head, change in total head actually here. Okay, so change in total head. Like for example, you can see this R is equal to, we have seen the change in static pressure head is nothing but half into 1 by 2z actually. Okay, so 1 by 2z times of u1 square minus u2 square plus vr2 square minus vr1 square. So this is actually the change in dynamic head, sorry, static pressure head. Okay, so this divided by 1 by 2z times of total head, which is v1 square minus v2 square plus u1 square minus u2 square plus vr2 square minus vr1 square actually here. Okay, so this is what you have as the expression for the degree of reaction in general. Okay, good afternoon Amit. Okay, so see here, in this case normally for impulse machines, normally in case of impulse machines are generally either tangential or axial. Okay, majority they are tangential or axial machines, means the flow effectively happens in these directions, tangential, or generally they will be also of axial machines. For impulse machines, what happens is R is equal to 0. Okay, so there won't be any effect in the change in the static pressure head. The whatever the direct impact or the impulse is there because of the fluid, that is only responsible for the fluid, like the case of the Pelton wheel. Okay, so we'll see what is this examples here. So we can write a good example as Pelton wheel here. Pelton wheel, this is actually a tangential flow impulse machine. Tangential flow impulse machine actually. Okay, and then in case of reaction turbines, normally you have to, again here also there will be certain things where the majority of the flow direction is axial, like for example in case of a fan. Okay, fan is a Kaplan turbine. Okay, normally if you see oils, this is axial basically. Okay, so the main flow direction is directed towards the axis of the main flow is directed along the axial direction. Okay, so axial flow reaction machines, axial flow reaction turbine is like a Kaplan turbine. You can see Kaplan turbines at a lot of places, like even all of you might have played with a Kaplan turbine since your childhood. Have you ever seen a Kaplan turbine? Have you ever seen a Kaplan turbine? Have you ever seen a Kaplan turbine actually? Any one of you? You have seen definitely in your life. No, you all have seen Kaplan turbine. Yes, normally fan. axial machine. Okay, of course it is not a turbine, it's a fan actually. Okay, but you might have seen generally in your childhood you might have played with this toy actually. Okay, normally people put it in front of the cycle. There's a straw, normally the straw what you drink the cool drink, so a straw, and to that a small fan is connected, and in your childhood you might have hold this fan and started running, and this fan will rotate. Have you seen this? Have you seen this? Yes or no? There's a straw kind of thing, then there's a fan, small fan kind of thing, and when you are running this will keep on rotating. Correct? Have you seen this? Paddle wheels normally. You might have seen all these things, correct? So all these are generating Kaplan turbines actually. Okay, when you are running, basically it's an axial turbine. Okay, and whenever flow comes and the blades are designed at certain angle, so that whenever the fluid actually passes through them, it rotates. Okay, so the fluid will actually impart some power onto this. At different locations you might have seen. So all of you, there's nothing like no one might have seen Kaplan turbine in your life. You might have seen. Okay, but the main thing is you don't know that at that point of time it's a Kaplan turbine. Clear? So anyway, it's an axial flow reaction turbine, Kaplan turbine, and also we have radial flow machines which are very powerful again. So centrifugal machines and all generally. So a radial flow reaction turbine, which is one good example, which majority of you already know the name, Francis wheel. So it's a Francis wheel or Francis turbine, you say, come sometimes. So all these are the cases. Okay, now we used to make it also with a dried leaves. Yes, exactly, fixing to a toothpasting. Correct. Toothpick, yeah, with toothpick you generally pick that. So anyway, so for impulse machines there won't be any pressure difference. So in general for impulse machines reaction degree of reaction, or it's also called reaction ratio sometimes, R is equal to 0. For reaction machines, this R is completely 0 less than R less than 1 actually. 0 less than R less than 1. Now can anyone tell me something? Lawn sprinkler, normally if you see a lawn sprinkler, this is an impulse machine or a reaction machine. What do you think, which is responsible for the reaction change? Or I told the answer, this is a reaction turbine, because you clearly see at the inlet the velocity is actually present. Whatever the velocity is there, same velocity will be there at the outlet normally. Okay, so you can see, for example, let us say if I have a lawn sprinkler like this, then if this lawn sprinkler is rotating about this axis, whatever is the velocity of the flow going here, same will be the velocity of the flow going here. Yes or no? Let's say for example if I take a single arm lawn sprinkler, then clearly whatever is the velocity of the fluid at this location V1, same will be the velocity of the location, because the pipe is of uniform diameter. Okay, but clearly the pressure at these 2 points will not be same, it will be different, because of which actually the lawn sprinkler will rotate on its own. Do you have anyone seen putting a motor to a lawn sprinkler and rotating it? No, correct? The lawn sprinkler, when fluid jets get gets out of them, the sprinkler rotates by itself, and the torque responsible for the rotation is provided by these jets. And this analysis, if you follow clearly, the dynamic head will not contribute anything for the rotation of the lawn sprinkler, because if here it is V1, here also it is V1, same pipe. Okay, so from continuity you can see V1 and V1 fluid jet, but because of the pressure difference, what happens, this will actually impart certain angular momentum or torque to this lawn sprinkler actually. Clear? So can anyone tell me, now you understood kinetic dynamic head is not responsible for this, so it's clearly a reaction turbine, a reaction machine. Can anyone tell me what is the degree of reaction for this lawn sprinkler? I've just given you some hint. I told you, since velocities are not contributing anything, whatever is the rotation, that rotation is purely due to the pressure change of the fluid. So can anyone tell me what is the degree of reaction of this lawn sprinkler? In this formula, if you see, this term is 0, V1 is same as V2, correct? Yes or no? Whatever is the velocity that's coming in, same velocity the fluid will leave the sprinkler. So V1 is same as V2. If V1 is same as V2, then what can you understand? What is the degree of rotation? Sorry, what is the degree of reaction of a lawn sprinkler? It's 100%. Okay, so degree of reaction of a lawn sprinkler is 1 actually. 100%. Okay, all these are simple fundamental things which you see day to day life. Got it? Okay, clear? So this is how you actually calculate power developed by any turbine. In case of reaction machines, one important thing they do, what they do is, I would like to tell you. Do anyone have ever seen a Francis wheel? Normally if you take a Francis wheel, normally Francis wheels are horizontal. If they, because of heavy weight and all, they'll mount them horizontal. So let's say fluid, this is a wheel, for example, this is the axis, and if the wheel is rotating like this, okay, and you have a lot of blades like this on the wheel, clearly, you know, fluid enters at some location like this, okay, so fluid enters at some location, then clearly you can understand fluid, if you observe carefully, fluid actually falls to the center, means basically at outlet R2 is equal to 0, and also fluid, it's not very 0 at the blade at 0, it's very small actually, but blades are purely radial. Blades are purely radial, means if you take beta 2, this will be 90 degrees for Francis. For Francis. Can anyone tell me why? Why such a construction is done? Normally, do you know this point actually? In case of reaction machines, generally the blades will be turned completely radial at the outlet, so that means basically this beta 2 blade angle at the outlet is 90 is what they made. So can anyone tell me why? Any idea what happens if beta 2 is 90? I'll give you a hint. You can see these triangles for some time and then tell me. You can see these triangles. Also, you know one expression which is H is equal to power delivered to the rotor is VW1 U1 minus VW2 U2 by 2Z is the delivered power delivered per unit weight of the fluid to the rotor. Power delivered per unit weight of fluid. Power delivered per unit weight of fluid. So can anyone tell me what is the advantage if this beta 2 is 90? Something happens. If beta 2 is equal to 90, something happens in this expression. What is that? Think. Come on, you guys can do it. Think. Yeah, exactly. No. VW2 increases. See carefully what happens to VW2. I'm telling beta 2 is 90, not alpha 2. Okay, this is alpha 2 actually, but I'm not talking about alpha 2. I'm talking about beta 2. If beta 2 becomes 90, what happens to this VW2? If beta 2 becomes 90, what happens to VW2? I've asked the question directly. Sign component will become 0. What is the sign component? Actually, this U is anyhow unavoidable. Okay, so U is always there. So this at beta 2 is equal to 90, and the outlet is made completely radial, purely radial, then clearly this VW2 is 0. Okay, and clearly this is a positive quantity. For this to maximize, this quantity should go to 0, which you can do. One thing you cannot do is, you cannot make beta 2 negative. Okay, you cannot twist the blade completely, then complete flow will stop. Okay, when it goes beyond 90, even 90 is not the most possible case. Normally it will be like somewhere around, this beta 2 is made around 15, 16, something like that, because sign component is very less at that case. But the main important thing is what happens here when you make this VW2 0, it would give you the highest efficiency. That's why in case of Francis wheels, something that you can see is normally outlet blades are purely bent radial. Okay, so anyway, this is some different story of this. So we'll go to the case of different machines now. For impulse, like we'll see Pelton wheel. For reaction, we'll see Francis wheel and Kaplan, all these things. But before going further, I want to talk about one very important things: dimensional analysis of a turbine, of any hydraulic machine in general, of a hydraulic machine. This is one very important, and majority of the many questions will come on this. Basically Reynolds transport theorem, impact of jets, all these things are again from the same basic story of inverse transport theorem, degree of reactions, then again these velocity triangles, few questions actually comes out. But one majority type of questions you might have seen in gate examination is the turbine, a full scale model of a or a 1/5 scale model of a turbine is developed under a head of 10 meters. What is the power developed by the model, power developed by the turbine? Lot of things they ask you, correct? Have you ever seen these questions? If you open your PYQ book, half of the questions will be of this kind. They'll ask you any hydraulic machine, they'll tell you some name, Pelton wheel, Kaplan turbine, or Francis turbine. They'll tell you a model of a Francis turbine is developed under a head of 10 meters. The actual turbine works under some 50 meters. So what is the power developed by the model? These kind of questions they'll ask you. Have you ever seen this? Okay. Clear? Now let's try to understand few things in the dimensional analysis of a hydraulic machine. In any hydraulic machine, normally in case of turbines or even in case of compressors or pumps, the power requirement or the power delivered is of most important. Like for example, if it's a turbine, then what is the power developed by the turbine? If it's a compressor or a fan, what is the power consumed by the compressor or fan? These points are very much important. Okay, so power in general for any hydraulic machine is a function of rotor diameter, ultimately the speed at which this rotor diameter will rotate, then the discharge, what is the flow going into the channels, then you have the potential head GH, then after you also have the fluid properties like O, mu, viscosity, elasticity, bulk modulus of elasticity. You can have a lot of things like this. Okay, so normally because in some like the cases what you told in case of gas turbines and all, the fluid can undergo certain compressibility effects. Okay, so for any machine, okay, so for any turbo machine, you can say for any turbo machine, P power, P is actually power delivered. Okay, so power, so power actually depends upon these quantities in general. Okay, you can keep still adding, but majority these are the quantities. Okay, now let us try to identify if you want to design a turbine, for example. Okay, let us suppose if there is some Pelton wheel in the field. Normally, do you know what are the diameters of Pelton wheels? Some 200 meters diameters are also there. Okay, so they are very such big massive structures. I can maybe show you in industries, which I think Pelton wheel man size. Okay, in industries, so Pelton wheel to a man size, for example, if you see, there are some figures I don't know whether I can correctly get them, but normally Pelton wheels are very massive structures in actual case. These are small Pelton wheels. I think even in your lab you might you can find a small scale, or Francis wheel, for example, Francis wheel to a, you have a lot of these are very giant massive structures. You can maybe see some locations. You see this is at some installation. I don't have a correct picture at the moment to show you maybe, but yeah, I can tell you. Yeah, here it is, some installation field. You can see this is a big massive structure, and this compared to this wheel diameter and all, you can see this is like 3 to 4 times of a human diameter. Okay, so you can understand the quantity of this. So anyway, this power is the case. Now when you want to design any models for your turbines, what are the things that are important? Okay, what are the, like for example, you see if you deal any movement of an object which is flowing inside a fluid, then clearly you will identify Reynolds number is the dimensionless number that should be same between the model and the prototype, like in yesterday's case we have seen. Similarly, in this case, what are the certain dimensionless numbers you should make equal between the model and the prototype if you want to design any hydraulic machine? Okay, so let's see. So clearly, let us, since the number of variables are, we can write this as some function of power, diameter, rotational speed, Q, GH, rho, mu. This bulk modulus, E is the bulk modulus actually, bulk modulus, which you generally see in the compressibility effects. Okay, and right now no heat, so only this is adiabatic, clearly adiabatic bulk modulus. Okay, so this is E. This function is equal to 0. Since there are 8 variables, it's very difficult for us to go through Rayleigh's method, so we'll use Buckingham-Pi theorem method. Okay, you can even use Rayleigh's, but anyway, the constants and all will be much better calculated in case of Buckingham-Pi, so we will go for Buckingham-Pi theorem method. Okay, so let's visit Buckingham-Pi theorem method. Then you know what Buckingham-Pi theorem method. Okay, so method. Now when this is Buckingham-Pi theorem method, let's check it out. Total number of variables is equal to total, how many variables are there? 1 2 3 4 5 6 7 8, right? 3 4 5 6 7 8 variables are there. Okay, now let us see the dimensions of each. Power, so power can be written as force into velocity. So force ml t power minus 2 into velocity meters, per second. So m L square T power minus 3 is what you have. This should be very careful, guys. If you make any mistake when writing the dimensions, calculations will change. Okay, so let's be careful. Force into velocity. Force is ml T power minus 2. Mass into acceleration. So this is velocity, meters per second. So m L square T power minus 3. Okay, fine. Then after diameter, it's very simple. It's meters, which is L. Then rotational speed. Okay, so rotational speed, normally we measure this in meters, in rotations per second. So angle doesn't have any units, but per second. So this is time inverse. Okay, so number of rotations per second. Okay, so did you all understand how we are making this? N is the RPM, normally rotations per minute. Rotations is just a number. Okay, so that don't have any dimensions. It's just a count per minute for some unit time, rotations per minute or rotations per second. You can see this is T inverse. Okay, now if this is T inverse, then you can see discharge, meter cube per second, meter cube per second. Then GH is the unit head. So GH, what are the units? G, meters per second square, into head, L square. Okay, so L square T power minus 2. So this has the dimensions of L square T power minus 2. Then density, kg per meter cube. Dynamic viscosity, SI unit, MKS, kg per meter second. So kg per meter per second. And bulk modulus, same as the dimensions of pressure. So Newton per meter square. So m L T power minus 2 by meter square. So m L power minus 1 T power minus 2. So these are the fundamental dimensions of any of these 8 quantities involved. Correct? So once please cross check whether I have made any L power, T power, something different at any place. Is it clear to all of you? These are the just dimensions of the fundamental quantities which are involved. Now tell me, these 8 quantities are in totally involving 3 fundamental dimensions. In all these terms, you can see either there is mass, length or time. There is nothing out of any other 4 fundamental dimensions. You don't have any temperature, you don't have any current, luminous intensity, mole, nothing is there. Only m, L, T are there. So clearly, number of fundamental dimensions involved. Number of fundamental dimensions involved. Number of fundamental dimensions involved is equal to 3. Correct? We have only mass, length and time. So therefore, as per Buckingham-Pi theorem, total 8 variables are there. These 8 variables are involving 3 fundamental dimensions. So how many dimensionless terms, how many pi terms I can generate? Please tell me. Number of pi terms is equal to, number of pi terms is equal to, can you tell me how many? There are 3 fundamental dimensions which are involved, and total there are 8 quantities. 8 variables are involved in this function. Then what are the total pi terms we can have? M minus n, right? So 8 minus 3, which is 5. So number of pi terms is equal to 8 minus 3, 5. So you should actually choose repeating variables. So 3 repeating variables should be chosen. Okay, so 3 repeating variables out of these 8, because we have seen 3 is the case. Then in yesterday's class, I have told you one should define the flow geometry, or basically the characteristic dimension of the problem. One should denote the kinematic parameter, and one should actually denote the one should actually denote fluid properties. Okay, so out of this, let us start picking. So for diameter, we can pick D. This denotes about the characteristic. Then let us take Qn also, because it's also some notation of kinematic parameter, number of rotations per second. So it talks about kinematics. And then density let us take, because it is simple to analyze. Because if I take mu, I have to use this T also every time. But if I take density, slightly smart, this time won't be there. So calculations will be slightly simple. That's it. Okay. So let us pick these 3 as the repeating variables. Did you understand? From yesterday's class, in yesterday's class, when I've taught you Buckingham-Pi theorem, I've spent enough time on deciding to choose repeating variables. Okay. So using the same technique, I have picked 3 repeating variables here. Can you see how I picked D, N, and also density? Yes or no? So please type in the chat box. Is this clear to all of you? 𝐂𝐬𝐧𝐤𝐬, Shivam, Vivek, Premraj, all of you. Is it clear how I have picked those 3 as the repeating variables? Yes? Okay. Now let's start our analysis. So pi 1, let us pick the first term, pi 1. So these are density, n, and also rho. Okay, so these are the quantities. Now let us start with the first pi term. Actually, let us see what happens. So pi 1 is equal to d power a, n power b, rho power c into. Now what are the remaining 5? Let us pick p. Okay, so p power. So this implies m power 0. This is slightly laborious. We have to do for some 5 minutes. Diameter L power a, n t power minus b rho m power c into L power minus 3c, because kg per meter cube, okay, into power is what we have here. Okay, so power also has got certain dimensions. What are the dimensions of power? M L square t power minus 3, m L square t power minus 3. So this is what we have. So totally if you put the things together, 1 plus c, okay, so 1 plus c L power a minus 3c plus 2, okay, and t power, sorry, this is t power and minus b minus 3, minus b minus 3 is what we have. Okay, so these are the dimensions. On the left hand side, clearly there are no dimensions. This is dimensionless, L naught t naught. If you equate the things, let's see what happens. C is equal to minus 1, clearly b is equal to minus 3. So this gives you a minus 3c plus 2 is equal to 0. So a minus 3c plus 2 is equal to 0. So a is equal to minus 5 actually. Okay, so a is equal to minus 5. Therefore the first dimensionless term that should be equal between the model and the prototype is p d abc, all are negative, correct? So p by d power a, so a is minus 5, so d power 5, then n power b is minus 3, so this is 3, and rho power c is minus 1, so this is 3. So the first dimensionless term that you get is p by rho n cube d power 5. You might have seen this term. Whenever you want to calculate power, you keep on equating these things. सर प्रॉपर्टी में n क्यों लिए? n प्रॉपर्टी नहीं, काइनेमेटिक पैरामीटर में लिया था, ठीक है, क्योंकि 1 मिनट में कितना रोटेशंस होते हैं. So it talks about the kinematics of the problem. Okay, so that's why you have taken n. If you want, you can take discharge also. Things go fine, no issues. Okay, because since velocity is actually involved in the discharge, so you can take that also, no issue. But since this is more fundamental in kinematics, I have taken. Okay, E lena chahiye tha. I just want to show you one thing, so that's why I have taken E. Okay, so let's see. Pi 2 is equal to again d power a, n power b, rho power c, and what about the other term? Let us take p is done, d n q. Let us take q then. Okay, so q, if you do this simple sort of dimensional analysis, m l t power zeros, l power a, t power minus b, m c l 3 minus c, q is again meters cube per second, so meter cube per second. Okay, so this is the discharge. So if you simplify, m power c, l power a minus 3c plus 3, t power minus b minus 1, this is what you have, and the left hand side is dimensionless. Okay, so now let's see, b is minus 1 clearly, so c has to be 0. So if you put c is equal to 0, a equal to minus 3, correct? So this term gives you pi 2 is equal to q, then a is negative, b is negative, c is 0 anyhow, so d power a, so a value is minus 3, so d cube into b is minus 1. Okay, so b is minus 1, n power b, so b is actually here, so n power b, c is 0, so a power c, that is 1. So this implies your pi 2 is equal to q by n d cube. So this is another dimensionless term which is actually equal. Okay, so that's pi 2 actually here. So pi 2 is q by n d cube. Similarly, let's do for 3. Okay, it just take 1 minute for each. Okay, maximum 5 minutes you can do. So pi 3 is equal to, again I'm just writing directly, m power 0, l power 0, t power 0 is equal to l power a, t power minus b, m power c, l power minus 3c into, what is the last quantity we shall take here? Q is also done, so gh. So gh has the units of l square t square, so let us substitute here, l square t square is what we have. Okay, so that's gh. This last term corresponds to gh. Here the last term corresponds to q. Here the last term corresponds to, this term corresponds to p. That's it. Okay, remaining things remain same. So if you simplify here, m power c, l power a minus 3c plus 2, t power minus b plus 2 actually here. So if you simplify this, then clearly b is equal to 2, c is equal to 0, because left side is dimensionless, and if c is equal to 0, then definitely a is equal to minus 2. Okay, so the term pi 3 is equal to the last term. Okay, so this is, what is the term we have taken? Gh, right? So gh by, then l power a, so a is the power of d, so it got d power minus 2, so d square. B is the power of n, so b is coming out to be 2, right? So b is coming out to be 2. Just a minute, let us check carefully. This is t power minus 2, no? Actually, yeah, t power minus 2, right? So this is t power minus 2 actually. So that means this is b minus 2. Okay, so this term if you make it 0, then clearly this is minus 2. Okay, so you have n square, and C is 0 anyhow. So this is the third pi term actually what you get. So this is the third pi term, GH by n square d square. Let us do the fourth. M power 0, L power 0, T power 0 is equal to L power A, T power minus B, M power C, L power minus 3C, because density power C is what we have taken. Then the last term, okay. So GH is done, density is already chosen, mu. Let us take mu actually. So if you take mu, mu has the dimensions of M, L power minus 1, T power minus 1. So if you segregate them, 1 plus C, L power A minus 3C minus 1, T power minus B minus 1. So this is the expression that you got actually, correct? So this is the expression that you have. Now if you make the things zeros, again C is equal to minus 1. So if C is equal to minus 1, A is equal to 3. No, it's not 3 I guess, right? C is equal to minus 1, so A plus 3 minus 1, so A is equal to 2. A plus 3 minus 1 is equal to 0, so A equal to minus 2, okay. And B is equal to minus 1 then in that case, okay. So B is equal to minus 1, then this implies your pi 4 is equal to mu by D power 2, because D is A is the coefficient of D in all the terms what we have taken, B is the coefficient of n, so n into minus 1 C, C is for the density, okay. So this is can anyone observe what is this dimensionless quantity? This quantity is something which you all know actually. That quantity is something which you all know. Can anyone tell me what is that? Can anyone tell what is this quantity? Yes, exactly. This is nothing but 1 by Reynolds number, okay. Because out of this product 1d, if you multiply with n, this nd has the dimensions of velocity. So this is like OVD mu on the top, okay. So this is nothing but your Reynolds number. One of the dimensionless numbers is actually your Reynolds number. Fine. The last thing let us do, M power 0, L power 0 and T power 0 is equal to L power A, T power minus B, M power C, L power minus 3C into last bulk modulus. We have bulk modulus. So what are the dimensions of bulk modulus here? You can check it quickly. Bulk modulus got M, L power minus 1, T power minus 2. M, L power minus 1, T power minus 2 actually. So if you simplify this, 1 plus C, L power A minus 3C minus 1, T power minus B minus 2. This is what you have, okay. So if you simplify, this B is minus 2, C is minus 1, no, C is minus 1 actually, yeah, C is minus 1, B is minus 2. So if you put C equal to minus 1 here, 3, A plus 3 minus 1 equal to 0, so A equal to minus 2. So this implies pi 5 is equal to this bulk modulus divided by d square n square rho n square d square. So this is what you have here, okay. So this is the dimensionless term. So these are the 5 non-dimensional terms which you got here, okay. So therefore for any turbo machine, it may be fan, compressor, turbine, whatever, for any machine, when you want to model the things, what you should do is actually you should make sure these dimensionless numbers, some function, maybe let us say capital F of pi 1. What is pi 1? So let's check. Pi 1 is P by rho n cube d power 5. So P by rho n cube d power 5, comma Q by n d cube, GH by n square d square, Reynolds number mu by rho n d square, and this guy is E by rho n square d square is actually 0. This is for any turbo machine, but in case of fluids, what happens is we generally don't take this viscosity in all the questions except last year XC1 question came, which made us even to get confused when giving the key. This you definitely don't take for hydraulic machines. For hydraulic machines you don't take, because in hydraulics we generally use fluids, okay. We use liquids, okay. So for liquids generally within the flow regime, this E compressibility effects is not much seen, okay. But last year theoretically one question is given. Normally for any machine these 5 quantities should be these 5 dimensionless quantities should be same actually, okay. Now let's see for case of turbines, for hydraulic turbines, what you can understand is normally we don't take viscous effects, but theoretically they can always give you a question on viscous forces. Last year XC it happened, they have given some variations in the dynamic viscosity and density something, okay. So you should be little careful in calculating powers, okay. So anyway, for hydraulic machines generally these quantities are important: rho n cube d power 5, Q by n d cube, GH by n square d square. And also, since last year that question came, I'm adding this Reynolds number. Ultimately, Reynolds number should also be there. So this is the main function. And for pumps, in case of pumps, normally here in this case, discharge is not much worried. So this is what you have. Okay. If I want to show you one important thing here. Why I have done a lot of hectic job is, if this is pi 1, if this is pi 2, if this is pi 3, and this is pi 4 ultimately. I just want to show you one thing. If you take the ratio of, consider pi 1 power 1 by 2 by pi 3 power 5 by 4. Okay. So let's say you have this pi 1 and pi 3. Now tell me one thing. If pi 1 is dimensionless, pi 3 is also dimensionless, then will this quantity have any dimensions? Please tell me. Look, pi 1 is actually a dimensionless quantity, pi 3 is also dimensionless. Then will this quantity have any dimensions? Will that quantity have any dimensions? No, correct. But if you try to understand carefully something, you can find something interesting here. Pi 1 square root, so that gives you p power 1 by 2 divided by rho power 1 by 2, n power 3 by 2, d power 5 by 2, multiplied with this power 5 by 4. So power 5 by 4 of this quantity, if you do that in the denominator, we have n power, normally this is n square, power 5 by 4. So that gives you n power 5 by 2, d power 5 by 2 divided by, because the main thing is I want to eliminate this diameter, that's it. Okay. So d power 5 by 2, okay, and g power 5 by 4 into h power 5 by 4 is what you have. Okay. So this is the quantity what you have, and in this quantity you can understand this diameter will not play any role, means I'm trying to eliminate the length scale. Okay. Now let's see if you're testing model and also the actual prototype in the same location. This quantity is actually equal to n power 3 by 2, n power 5 by 2. You can cancel this n times, okay, because this is 3 by 2, this is 5 by 2, a power m by a power n gives you m minus n, 5 by 2 minus 3 by 2 gives you n actually. Okay. So you have n times p power 1 by 2 square root of p divided by rho power 1 by 2 into g power 5 by 4 into h power 5 by 4. Okay. So you can see n root p by rho power 1 by 2 into g power 5 by 4 into h power 5 by 4 actually. So this is a dimensionless quantity. Dimensionless quantity. And this tells you something like, if you try to keep the dimensions, for example, okay, so this is a dimensionless quantity because this is just a simplification. This is called dimensionless specific speed actually. Okay. So what is this specific speed? You know, specific means per one unit, like specific volume, specific entropy. You have seen a lot of things. Now clearly this ns, normally if you see for turbines, normally call this nst. Okay. So this quantity is actually the dimensional specific speed of a turbine. Okay. Because you can see generally if you are testing with same fluids, if you are not using same fluids, then you cannot do this. But if you are doing same fluids, this density can be taken out, eliminated from this. And also if you are testing in the same location, this gravitational field can also be neglected because gravitational variations do not impact much actually. Okay. So you can see this value becomes n root p by h power 5 by 4. Okay. So this is h power 5 by 4, and this expression is very much important in determining the size of the turbine. Okay, because this gives you the speed at which the turbine should rotate for providing 1 unit power, under 1 unit head. Under unit head, if the turbine has to provide a 1 unit power, how much, at what speed it should actually rotate. Okay, so that's what you have. Up to what time we have class today? Oh my god. Up to what time you want? because World Cup match is also there, I understand, but still a bit of Pelton. Look, the principles are same. Basically, for Pelton wheel or Kaplan turbine or Francis turbine, this story of velocity triangles until this part is same. Okay, only the math changes. We'll try to take till 1:10. Okay, just 10 minutes. I know definitely the toss won't be done at 1:10. Okay, just 10 more minutes I'll take. Fine. Can I take just 10 more minutes? Fine. Till 1:10 we can take the class and we'll end. Okay, I'll discuss at least Pelton wheel in detail. Okay, because Francis and all, anyhow you know the same velocity triangles will hold, but beta 2 is 90. Okay, we'll see. Okay, so this is what we have for the dimensional. I think this is blocking this, so let me write this separately. Dimensional specific speed of a turbine. Dimensional specific speed of a turbine actually here. Okay, so this is the dimensional specific speed of a turbine, and you might have seen this expression N would P by H power pi by 4, all these things. We all will support India. Why not? Do you think I support some other nation? Even I support India. Okay, fine. Now anyway, let's see. This is what you have. Similarly for pumps, you can understand. Similarly, if you do for pumps, normally in case of pumps, discharge is of main concern and also power supplied has to be the main concern actually. So you will see N and Q. If you take these terms like Q and GH, okay, so pi 2 power 1 by 2 by pi 3 power, what is the constant here? GH power 3 by 4, I guess, right? Anyway, we'll find. If you don't know, we'll try to eliminate the diameter, we'll get the constant easily. So in this pi 2, what is the constant you have? D cube is there. So if you want to eliminate this, we should have power 3 by 2. Okay, so power 3 by 2. So anyway, since we are taking half here, so to eliminate 3 by 2, if you want to eliminate 3 by 2, because pi 2 power 1 by 2 is taken because root q. So if you want to eliminate d, so if you take power 1 by 2 here, we'll get d power 3 by 2. So there also, if you want power 3 by 2, you should take 3 by 4. Okay, so then you'll get 3 by 2. Yes, so 3 by 4. Let's take 3 by 4 here. Correct. Now if you do, after a bit of doing dimensional analysis, we will get N root q by density power half is what you will get. Then G power 3 by 4 is what you will get, and H power 3 by 4 is what you will get. Okay, so similarly, if you do the same things, like you are testing in the same gravitational field and also for the same fluid, we'll get Ns of a pump is like N root q by H power 3 by 4, because this Buckingham-Pi theorem analysis, what we have done is same for all the things. Clear? So anyway, you might have seen these things. Now quickly we'll go through one question of dimensional scaling so that you can understand this. Okay, so let's see, or else we'll do one thing, because time is a bit short. We'll try to solve Pelton wheel. Okay, before we go, we'll try to look at Pelton wheel. Then problems you please solve, and if you have the problem, please ask me in this group. Okay, so this is my Telegram channel, so you can just join in here and you can ask the questions. Okay, and anyway you can solve after this much of understanding of the basic dimensional flows, you can understand. Okay, then let's have a quick discussion of Pelton wheel. Okay, Pelton wheel. Okay, normally I have shown you how Pelton wheels look like. These are the Pelton wheels. Okay, so like you have a lot of buckets. Maybe this image is good looking. So you can see these are the buckets, and normally nozzles will be injecting the fluid jet onto this so that this wheel will rotate about this axis. Okay, now let's see, in case of Pelton wheel, it's a tangential flow impulse turbine. Tangential flow impulse machine turbine. It's of course a turbine. Okay, now let's see what happens. This is how the wheel is there. Practically, if you see, there are like lot of, it's a rotor hub, and maybe let me make an attempt. There are several blades. Okay, so you have the shaft. So this is the shaft, rotor shaft. This is the rotor, and on this rotor there are a lot of blades actually. Okay, and anyway, if you see, I'll just try to draw one of the blades. Okay, so this is the everything, and clearly you have the blade like this. Okay, so this is one of the bucket. So this is bucket. Similarly, you have plenty of buckets like this all over. Like here you can see, this is how you have a lot of buckets. I have drawn just one. Okay, now in this case what happens, the fluid jet will go and it actually comes out. You may not physically understand here, but if you see this diagram, I'll just show you. If you draw the top view of this, for example, you can see the buckets look something like this. Okay, so what's happening, the fluid will actually hit here, then it travels to the bucket and slides out. Okay, so you can see, for example, in one case, if I try to draw it properly, let us say if this is the bucket, some half of the bucket. Okay, so first half of the bucket, and this is the second half like this. Then when fluid goes here, the fluid hits this like this, and then it travels along the blade and it comes out. Okay, like you can see, the fluid hits here, then travel along the bucket. Like maybe I can show you one more plate where it's looking clear. Yes, in this diagram I think you can see it better. Just a minute, let me show you this. Here it is. Yes, so you can understand, normally the fluid hits it at the center, then travels to this and comes out. Did you understand how the fluid actually moves in this? Okay, so the fluid impacts here, splits into two parts and travel along the bucket and will come out at the same radius. That's how it actually comes at go in at a particular radius and comes out at a particular radius actually. Okay, so anyway, let's see if this is the radius at which it is doing these things. Then if you draw the velocity triangles of this, at the outlet what happens, let us say if this is the Peloton wheel, for example. Okay, so if you see the cross section, you will have the blade like this. So practically what happens, the fluid will enter like this, and then some part of the fluid will travel in this direction and comes out, and some part of the fluid will actually travel and comes out like this. Okay, and flow deflection angle, you can see, normally the fluid is supposed to go like this, but it's traveling like this. So this is the flow deviation which is happening, beta. Okay, so and clearly if this is beta, then this is 180 minus beta, which means this is also 180 minus beta, because this is the same line. So one thing that I would like to say here, this blade moves at u velocity, correct? This blade moves at u velocity because of this impact on the jet. This blade moves at a velocity u, which you call the blade moving velocity. Then if this is u, and if the fluid is coming at a velocity v1, then clearly the inlet triangle will just be a line here. Okay, so this is v1, out of which if some part is u, then the remaining part is nothing but the relative velocity. Okay, so this is u, and this is a relative velocity at location 1. Now whenever this is relative velocity at location 1, if the blades are smooth in general, so this velocity at which it comes out will also be same. VR2 is same as VR1. Like in case of jets and all, we have seen whenever there is no friction, nothing here, there is no reduction, then clearly what is the relative velocity it's sending, same relative velocity it should come out if there is no friction along the blade. Okay, and VR2, normally there is a ratio which is called the velocity reduction ratio, VR2 divided by VR1. This is the ratio of relative velocities, K, ratio of relative velocity. Okay, normally this value will be given 0.98, 0.99. It will be very close to 1 until and unless the turbine gets completely eroded. Okay, now let us see here in velocity triangles, from inlet triangle, one thing you can understand is, since this don't have any vertical components and all, this v1 is straight away equal to vw1. Yes or no? So please type in the chat box. Is this clear? In this case, since completely it's in the direction of the motion of this fluid in the tangential, so v1 is same as vw1 here. There is nothing splitting here. But in this case, there is certain deflection. Like for example, you can see, let me draw it a bit clearly. If the fluid is coming in this direction at VR2, and clearly it is coming at an angle beta, because this complete flow deflection is 1 beta. So for example, if you call this beta acute, okay, this is also beta. And clearly the fluid jet is moving in this direction, so this is your u. Then clearly the relative velocity is, the absolute velocity is v1, because this is the vector summation of vr2 plus u. Okay, and if you resolve this vr2 plus u, this component gives you v2. Okay, the velocity at which it is coming out. So vw2, so this is vw2 clearly, and this is vf2. Okay, vf2. Now let us see, since you should know what is the power which should be transferred to this Peloton wheel actually. So from outlet angle, from outlet to angle, clearly one thing is very sure. If you resolve a velocity which is in this direction, the x component of the tangential component will be in the negative direction, yes or no? Because completely the blade is moving in this direction, but this outlet velocity is in the reverse direction because the v2 is in this way. So clearly, if you call, for example, this angle as alpha 2, okay, then this x component of velocity or the tangential component vw2 will have a sense in the negative direction. Clear? So anyway, if you can understand this, then from outlet to angle, vw2 is equal to, in terms of magnitude, if you take vw2, this vw2 is nothing but, this is vr2 and this is beta. So vr2 cos beta is what you have as the complete length. From that you subtract your velocity. That's it. Okay, because the outlet and inlet are at the same radius, so u1 is same as u2, which is equal to u. Clear? Because from this center of rotation, the fluid is going in and coming out at the same radius, so there is no variation between these two guys. Clear till this point? Quick, please respond. Is this clear till this point? Yes or no? So please type in the chat box, is this clear till this point? Because if you want to calculate this length is nothing but the total length minus u, okay, and the total length is nothing but vr2 cos beta 2. That's it. Okay, so that repeat one last time. Yes, I'm repeating. Normally if you see this, if you see this, vw2 is this part of the length, yes or no? To get this length, what I'm doing, I am taking the total length minus this u, okay, and what is the total length? If this angle is beta, if this is vr2, so vr2 cos beta gives you the total length minus you are subtracting u from that. That's it. Okay, clear, Ladani? And also the direction is negative because v2 is oriented in this direction, for which if you resolve x, which is this component, this will be actually in the negative direction, like this. Clear? Then let's see. Therefore, if you calculate the head developed, so h is equal to vw1 u1, okay, vw1, this u is same, u1 and u2 is same in this case of a turbine, so this is g. So this is the head which we have derived from the basic Euler's equation. So h is equal to v1, because vw1 is same as v1 from this inlet angle, minus vw2. The magnitude of vw2 is vr2 cos beta minus u, of course this is 2, but this has to be put in a negative sign, so minus of minus will give you plus. Why I am putting this minus? Because this resolution will actually give a component of vw2 in the negative direction of this blade motion. That's why. Okay, so that's actually trying to reduce the head, so that's why it's negative of negative, multiplied with u divided with g actually here. Okay, now you can understand one thing. If you take v1 common, okay, if you take this v1 common, v1 square common, for example, or this u is there right now, let's check. If you see, therefore blade efficiency, if you talk about this blade efficiency, then energy supplied, okay, so you can write this vr2 as, look what you can write this vr2, for example, vr2 is equal to k times of vr1, and what about vr1? vr1 is nothing but v1 minus u, right? That's what you have here in this case. You can see clearly k into vr1, this v relative 1 is nothing but this complete v1 minus u. So if you replace here vr2 as k times of v1 minus u, let's see. First of all, the energy supplied per unit weight is actually v1 plus, okay, so v1 plus vr2 can be replaced with k times of v1 minus u cos beta 2 minus u, okay, so this minus u actually, okay, so this minus u divided by this quantity divided by u divided by g, okay, and to this you have a multiplication of u actually here, okay, so that's what you have. Now let's see one thing, divided by the total energy per unit weight, so v1 square by 2g, correct? Because normally if you see the kinetic energy of any fluid which is coming in, m is equal to half rho v square, then per unit discharge, so this is actually into discharge also, because density into discharge gives you mass. So per unit weight of the fluid per second, you will see you will be left with v1 square by 2g, okay. So if you do this as v1 square by 2g, you will identify from simple basic differentiation for maximum blade efficiency, if you write this d eta by d u by v1 is equal to 0. If you do this, you will find out u should be equal to half of this jet velocity. Okay, right now I'm leaving this for you. So yeah, I'll summarize. So could you also give overflow of flow or potential bodies if time permits? Actually, I've told something about this. For flow, this source, sink and all, we have uploaded lectures of potential flows actually. Okay, so for potential flows, I have already told you these lectures are there. Please go through them if you find some time in YouTube. If you go to 𝐂𝐸 English, 𝐂𝐸 English, if you go to this channel, okay, these are actually the detailed course lectures of potential flows, complete potential flows. Okay, flow past bodies, a Rankine body, okay, flow past cylinder, flow past rotating cylinder, source, sink, vortex, everything is there in this. Okay, so you go to videos. Okay, so you go to videos and you can see these are the lectures actually. So this is the first lecture, introduction to complex potential function, 1, 2, basic potential flows, superposition, your Rankine half body, flow past bodies, all things come here, 3, 4, 5. These are the 5 lectures, 1, 2, 3, 4, 5. Hardly this lectures are of 1 hour 30 minutes, 1 hour 45 minutes, things like that. So definitely you can go through them. It gives you the complete detail of fluid potential flows. Okay, fine. So this is what you get. Okay, and this is the total energy available with the jet at the inlet of the water. Okay, normally you can see this is nothing but head delivered by head available at water inlet. Water inlet. So this blade velocity has to be half of this jet velocity. You can do simple maths actually. Okay, this big cost beta 2 is constant, k is constant, v1 is constant. Okay, you can actually take v1 square common and you can delete this v1 square and this v1 square. You will have the function of u by v1 actually. Okay, so that's what you can do. So if you do that, then things gets eliminated. Okay, fine. So we are stopping it here. The only thing is reaction turbine. I'll do one thing because time is a bit short. We'll upload the notes about this Francis turbine in the Telegram group in a short period. Okay, I have the notes already of what I have taught. So Francis turbine notes, maybe I'll upload by today night. So Francis turbine, like why the casing is actually spiral, not completely circular. We'll deal a lot of things in that. Okay, and yeah, since someone is asking me to summarize, I'll have a summary at this point because the time is up. So what we have done, we have seen a bit of turbulent flows. Of course, I have opened my notes and I have explained you. But anyway, coming to this turbo machines, in this Euler's equation, for rotation of this disk, I've told you this tangential component VW, which I have written there. So that should be important in this case. And from RTT, we have seen how the angular momentum equation for the turbines comes out. This is not only for turbines, for any turbo machine in general. And we have seen a bit of funda and velocity triangles. I have explained you how you can actually convert this, how to draw these velocity triangles, and also this power is again the same expression. Then after conversion of these velocity triangles into this term. Okay, so how this VW1 U1 can be converted to this term, I have explained you here using dot product example, and I have shown you. Now this is directly due to the change in dynamic head or the kinetic head of the fluid, and this is in the pressure head. Okay, and if you see certain differences, degree of reaction I have defined. Then this is one normal common example what we see. This is a 100% reaction machine, lawn sprinkler, and we have done certain dimensional analysis if you want to scale the models, how to do. So these terms are the 5 important dimensionless terms, which these terms are the 5 important, these are the 5 important dimensionless terms for any hydraulic machine in general, which we have seen from Buckingham pi theorem analysis. And we have seen the concept of specific speed as well, and Pelton wheel we have seen, but because of time constraint, I'm leaving the Francis turbine. I'll upload the notes in Telegram. Okay, so notes in Telegram channel. It's like t.me/pw. When I is where you can search it. Okay, so that's my Telegram ID. You can just join there. By the evening, I'll try to post the Francis turbine notes. Okay, you have certain logics. Okay, everything what you do, you have certain logic and certain physics developing that logic. It's not like since I like n over p so much, I take n over p by h power 5 by 4, nothing. You have to eliminate the diameter, means independent of the geometry of the machine, what speed the machine should operate for generating 1 unit power. These are the important understanding that you should make when you're doing turbo machines. Similarly, in heat transfer, when you're doing about Prandtl's number or Grashoff's number, why these numbers are important, why these dynamic viscosity and density combinations are important, why kinematic viscosity is important in fluid flows when there is heat transfer, all these points are important. Okay, so everything you should learn conceptually. Okay, that's what I finally want to say. Anyway, there are some quick questions. You can always keep trying these questions, and at any point if you can't solve any question, you can again discuss in that group. So we talked about what we talked about today. Turbulence, we have introduced some basic bit of ideas, and then hydraulic machines like Pelton wheel, all these things we have seen. Okay, look, whatever the machine, it's a radial, Francis, turbine or impulse, anything is fine, only this analysis is common. Okay, so this is what you should understand in terms of velocity triangles. Maybe if it's a Francis wheel, you might have some different velocity triangles. At Pelton wheel, maybe this triangle may get converted to line, that's it. Okay, so depending upon the type of turbine, these triangles will change, but this fundamental and this equation will never change for any turbine, whatever the turbine you take. Clear? Okay, so that's fluid mechanics for now. Okay, and definitely I think there will be a marathon session of revision. Maybe if I may take, or Shivam sir may take, any one of us will take generally, and you can learn all these points in a together thing. Okay, today I think without any break we have went very fast because this is the last lecture and I thought of promising you finishing the things. Okay, fine. I hope you all got benefited from this course at least to some extent. And are you all feeling confident when you're solving PYQs? Because with this knowledge what I've given you, you can easily solve PYQs very easily. Okay, so anyway, thank you all. We'll meet sometime later. Okay, very soon we'll try to meet again on YouTube channel, because anyway, when GATE exam nears, we have a lot of things to do. Fine. Okay, and for potential flows, please go for that. I'll try to upload it for compressible flows as well, so that you have 100% with you. Or compressible flows, if Vinod Sai is taking ATD, I'll request him, he'll take, or if I'll try to find some time and I'll take the compressible flows. It's fine, anything is fine. Okay, wholeheartedly thanks a lot. Yeah, sure, thank you. Okay, so we'll meet soon. Take care, bye, signing off.